So we're going to finish off the cardiorespiratory unit by talking about the challenges that are faced by the respiratory system. And so there are four main challenges that the respiratory system has to overcome during exercise. And so each of these videos is going to talk about one of those challenges. So with this first one, though, we'll identify the four challenges and we'll explain the first one and how it deals with that specific challenge. And then each of the videos will go into detail about how the respiratory system overcomes or handles that challenge. So the four challenges to the respiratory system are as follows. We've got to make sure that, or we've got to adjust for the fact that there's low oxygen and high CO2 in the venous blood going back to the lungs. The fact that due to increased cardiac output, pulmonary blood flow will increase. But as a result of that, there's an increase in vascular pressure. Okay, and so when we talk about vascular, we're talking about the vessels. So there's increased pressure inside those vessels, and there's consequences to that if we can't adjust for it. As a result of the increased cardiac output, this leads to increased pulmonary blood flow. That blood is moving through the pulmonary circuit much more quickly, much quicker. And as a result, there's less time available for diffusion to occur. And then the last one is the fact that when we're at max exercise, we might be breathing 20 to 30 times more than normal, and that requires oxygen, that requires energy, and so we have to divert some of the blood that would go to active muscle. We have to divert that to the lungs, and there's challenges with that. So let's talk about the first one. So we've got low oxygen and high CO2 in the venous blood that's going back to the lung. And really what we're trying to do is protect alveolar oxygen and alveolar CO2. So we don't want alveolar oxygen to get low. We don't want alveolar CO2 to get high. Okay, and so we've got a figure here, and I want you to take a minute and just look at this figure. What do you see going on? Okay, and let me orient you to it. So on the x-axis, we have VO2 max, so you could just think of it in terms of exercise intensity. And then on the y-axis, we have pressure of oxygen. We've got two lines here, so P little a O2 is arterial oxygen, big A O2 is alveolar oxygen. And so what do you see here? And so as you look at this, notice that arterial oxygen remains relatively constant. It does increase a little bit after we get to about 60-70% of max. However, alveolar oxygen goes up tremendously as we get halfway or maybe a little bit more. We're actually hyperventilating here. Okay, so we're bringing in more oxygen than we're going to use. So why is that? And part of that has to do with, we mentioned earlier the lactate threshold. Remember, we build up hydrogen ion when we're exercising, so we become more acidic. Well, one of the things that we can do is we can help get rid of acidity by increasing our ventilatory rate. Okay, and so this kind of ties into the oxyhemoglobin curve. Remember that we have a right shift when we have high CO2, high hydrogen, and or high temperatures. This is all true in the muscle cell. So we have that right shift, which is great because it allows us to unload oxygen. All right. And so as a result, what's happening is with the greater amount of CO2 produced, hydrogen produced, greater temperature at higher intensities, we actually get rid of more oxygen. Okay. And so as a result, this leads to low oxygen returning to the lungs and high CO2 in the blood that's returning to the lungs. So just a quick refresher from last week about carbon dioxide transport. Remember, we transport it three ways. As bicarbonate, it can be bound to hemoglobin, which means it's displacing oxygen, or it can be dissolved in the plasma. Okay, where does this CO2 come from? Or, excuse me, the CO2 comes from the tissues, the active tissues. At rest, we produce about 3 milliliters per kilogram per minute. So in a typical adult, that's 200 to 250 milliliters per minute. Okay, and during exercise, though, we can increase that by 20 to 30 fold. And so we go from 200 to 250 mils per minute to upwards of 4 to even 7 liters a minute. And obviously, this is dependent on the exercise intensity as well as the size of the individual. A bigger individual is going to produce more CO2 than a smaller individual. So how do we maintain this? And how do we protect these values or the oxygen and CO2? Now we talked about this equation earlier in the unit. Remember, this is not something that you'll ever need to use. Like, I'm not going to give you numbers and you calculate it. But alveolar oxygen is affected by many different things. So most of these are going to stay constant as we exercise. The fraction of inspired oxygen is going to stay constant at about 21%. Barometric pressure will remain constant unless somehow, some way, in the middle of exercise, you go from sea level up on top of a mountain. The pressure of water at 37 degrees is always going to be 47. So really the only two things that will change are arterial CO2, which is going to be dependent on how much CO2 you're producing in the tissues, as well as your RER, which in essence takes into account, it's that ratio between oxygen utilization and CO2 production. Okay, and then CO2 is primarily dependent on how much CO2 you're producing, and then your alveolar ventilation. So if we look at CO2, if I produce more, I'm going to have a higher alveolar CO2. But I can offset that by increasing my alveolar ventilation. All right. And alveolar ventilation is indirectly related to RER. So if I breathe more, if I hyperventilate, my RER will actually go up. So look at this figure here. Got another figure for you. And so what I want you to do is just look at, we've got exercise duration here on the x-axis, and I don't know why my toolbar is showing up. I'll try to get rid of that. It doesn't. But we've got different intensities of exercise. And so look at pulmonary or minute ventilation on the y-axis, and then just look at where ventilation is during each of these three different exercise bouts. Okay, at rest, we're normally about 6 liters per minute. Max exercise in a typical adult, 120, maybe a little bit more. I've actually seen individuals at 200 plus liters per minute. It was a very fit individual that was a pretty big guy, bigger than me. So I think he was like 6'4", 205. And so he was getting up to above 200. Now, there is a measure that would actually be kind of fun to do. It's called maximal voluntary ventilation. And this is just when you have a person breathe as fast as they can for as long as they can. And you measure how much they're actually breathing. Okay, so even at max exercise, we're not really that close to how much we could actually bring in. Okay, so during max exercise, a person might be at 125 liters per minute. But if we allowed them to breathe as much as they could, as fast as they could, they'd likely hit 200, and that's almost 40% above. Okay, but I think it's also important to note that for each bout of exercise, once you hit steady state, or once you're used to that exercise, you're bringing in the appropriate amount of oxygen, getting rid of the appropriate amount of CO2. Excuse me. That for the most part, ventilation remains flat. Okay, and so we've got hyperpnea and hyperventilation. So if you remember back from your intro to physiology class, hopefully you remember the difference here. So hyperpnea is where we increase ventilation to meet metabolic demand. Okay, we do that for the first half, maybe a little bit longer of exercise. Notice that ventilation is going up, and it's going up kind of in proportion to the amount of CO2 that we're producing. But we reach this point here, it's sometimes referred to as ventilatory threshold, and oftentimes it coincides with lactate threshold, where now we're hyperventilating. Our ventilation is exceeding what is needed for metabolic demand. Okay, and so what's not shown here is that as this line goes up at a steeper slope, our CO2 in our arteries is actually going down. Okay, we're breathing off more CO2 than we're producing. And again, this goes back into the fact that we're trying to buffer or balance out the increased acidity that occurs with exercise. And so how do we maintain our alveolar oxygen or alveolar CO2? Well, for the most part, we just increase our ventilation in proportion to those changes. But at the end of exercise, or at the end of max exercise, or near max exercise, we actually start to breathe more in an effort to balance out or maintain our arterial pH. And so, just to kind of put this in words, we increase our ventilation in proportion. And why or how? Well, we've got the same stimuli when we exercise that we do when we're just sitting here. So we've got CO2 production, we've got oxygen production, we've got hydrogen ion production. All of these things will cause us to breathe. So if we have high CO2 or high hydrogen ion, which means a low pH, we're acidic, we're going to breathe more. If we've got low oxygen, we're going to breathe more. Now, generally speaking, as you're sitting here watching this video, what's causing you to breathe is CO2. But as we exercise, CO2 goes up, hydrogen ion goes up, and oxygen goes down. So now we've got increased stimuli. So our current hypothesis as to how or why this happens is at the beginning, and we've talked about this before, we talked about it earlier in the week with central command. Remember, if you're on the starting line getting ready for a race or waiting for a football play, to start, or whatever you're doing when it comes to exercise, when you're standing there, your metabolic demand hasn't changed. However, your breathing rate, your heart rate, all of that has changed. And this is due in part to central command. Your body, different systems in your body are talking to each other, letting them know exercise is about to occur, and so we're going to need more oxygen. All right. And then as you start exercising, you produce more CO2, and that allows your body to fine-tune, kind of hone in on exactly how much your ventilation needs to increase. So this becomes the negative feedback loop. All right. And so okay, so I figured out how to get rid of the taskbar real quick. So what you can see here is that when we start exercise, our arterial CO2, pH, and PO2 relatively normal. These values are a little lower than what we talk about, but I think you'll get the idea. Okay, and so what's happening is when we have this hyperpnea, our CO2, pH, and PO2 remain constant. However, when we hyperventilate, we're actually getting rid of more CO2 than we're producing. Notice that we go down from 40 to 30. Our pH goes down because we're becoming more acidic. And so we're trying to balance out this increase in acidity by getting rid of CO2. So how does this happen? Well, we've got chemoreceptors that monitor these changes in pH. And then we've got the hydrogen ion that's coming from muscles. And we come back to this equation that I know that I talked a lot about in 220. So we've got carbon dioxide and water combined to form carbonic acid, which can then break down into hydrogen ion and bicarbonate. Hydrogen ion is what determines how acidic something is. Bicarbonate is alkaline. And even though we're producing both of these things, one's an acid, one's a base, generally speaking, we'll hold on to one and get rid of the other depending on what's going on with our pH. And so what's happening is we're producing excess hydrogen ion from our muscles, and so we become acidotic. And this is considered a metabolic acidosis because this is coming from the muscles. This has nothing to do with the lungs or the respiratory system. But because we're breathing more, we would say the respiratory system's trying to compensate. So we say respiratory compensation for a metabolic acidosis. Now, this hyperventilation seems to occur with the rise in lactate because eventually there comes a point where we can't clear out as much hydrogen ion with lactate, bring it out, buffer it as well. And so that's why we believe that these ventilatory threshold and this lactate threshold kind of correspond. We really haven't gone into lactate threshold, but we will in a couple weeks. And so we'll try and tie these two together. But what I really want you to know at this point is that the ventilatory threshold and the lactate threshold occur at about the same point. And so when I'm talking about the ventilatory threshold, I'm talking about this point right here where we go from this linear increase and then we kind of have a spike, or our slope changes. And so that is the end of the first respiratory challenge.